Hello friends, welcome to Physics Live channel. Today we are discussing about statistical mechanics. So, statistical mechanics is a connection bridge between thermodynamics and quantum mechanics, because thermodynamics is a macroscopic point of view and quantum mechanics is a microscopic point of view. Statistical mechanics is the connection bridge between this thermodynamics and quantum mechanics. So first of all, you have to know about the macroscopic variables, in which what do you mean by extensive? Extensive, this is depend on mass. Intensive, independent of mass. And here we are discussing about position and momentum, that is macroscopic variables. And the phase space, it is space of real space plus momentum space. Momentum space. So if you consider the phase space, this is momentum, this is position. So if you consider a point qi pi, that is position and momentum. Okay, so then also you have to consider some equations to find the dimension of phase space and also the volume of unit cell. So if you consider n number of particles, n, and dimension of phase space n number of particles, degree of freedom, that is f. So the dimension of phase space is 2fn. Volume of unit cell is h power fn. Okay, so this is the formula. Dimension of phase space is 2fn and h power fn is the volume of unit cell. And also we have to consider the density of states. Density of states, that is d omega by dE. So what is omega? Omega is a number of accessible states, that is number of microstate, that is omega, that is Vp into Vq divided by h power f. That is Vp is the real volume and this is Vp is volume of momentum and this is volume of real. H power is f is volume of unit cell. That is total volume of the phase space divided by volume of unit cell will give you the number of accessible states, that is number of microstate omega. For n particles, omega n is given by omega 1 all power n. So omega 1 is this and omega 1 all power n is omega n. Okay, so this is all about the microstates. Number of microstates is given from the phase space, that is total volume of the phase space divided by volume of unit cell. Volume of unit cell is given for one particle, that is h power f, and volume of phase space is momentum space into position space. For position volume, so you got the total volume of phase space, and from that we arrived at the density of state, that is d omega by dE. So if you consider, we can consider any one dimensional, two dimensional and three dimensional cases, and in which you can consider the non-relativistic and relativistic case. For that you got the density of states. We have a trick, that is density of states is directly proportional to e power d by s minus 1, where d is the dimension and s is a value for which, that is E is directly proportional to P power S, that is energy is directly proportional to P power S, in which S is taken as in this formula. Okay, and this will give you e power d by s minus 1, that is given by density of states proportionality. This is this is a relation of density of states with the energy, how it related. So there is a question that is density of state is directly proportional to E over 1 by E. So we have to find the relation. So for that we have to use this e power d by s minus 1. For d is the dimension and this is equal to the value in which E is directly proportional to P power S. So we know that in non-relativistic case E is directly proportional to P square by 2m. So E is directly proportional to P power S means P power 2. S is equal to 2. So when we consider the one-dimensional case, so D is equal to 1. So density of state is directly proportional to E power D by S, that is D is 1, S is 2, 1 by 2 minus 1, that is E power minus half. Density of state is directly proportional to e power minus half, that is the answer. So from that you can also substitute two-dimensional d equal to 2, and for relativistic case E is directly proportional to p square by 2m, so s is equal to 2. So density of state is directly proportional to e power d by s, that is 2 by 2 minus 1, so e power 0. Okay, and also non-relativistic case E is directly proportional to pc. E is equal to Pc now. So E is equal to Pc, E is directly proportional to P power 1. So S is equal to 1. So E power D by S. For two-dimensional D is 2, S is equal to 1 here, minus 1. That is 2 minus 1 E power 1. So likewise we can find the relationship between density of state and energy. Okay, so this is the introduction for statistical mechanics. In this study we studied about what is the dimension of phase space and how to find that, and also volume of unit cell, that is h power fn, dimension of phase space, that is 2fn, for degrees of freedom is f and n is number of particles, and density of state is directly proportional to e power d by s minus 1, where s is the proportionality of E is directly proportional to momentum power something, that power is known as s. Okay, and what is Liouville's theorem says that, what is the Liouville's theorem? Liouville's theorems, that is Liouville's theorem states that, what is meant by Liouville theorem? That is density of phase space is a constant. That is density of phase space is constant. That is explained in Liouville's theorem, that is d rho dou rho by dou t. Dou rho by dou t is equal to 0. Density of phase space is equal to 0. So in which the equation of continuity we know that del dot j plus dou rho by dou t is equal to 0. So dou rho by dou t is equal to 0 from this Liouville's theorem. So del dot j is equal to 0. Okay, dou rho by dou t equal to 0, so del dot j is equal to 0. Conclusion from the Liouville's theorem, that is density of phase space is equal to 0. That is, they studied about Liouville's theorem, in which they have studied, that is del dot j is equal to the Poisson bracket of rho comma h. Okay, so they find the equation of continuity. Equation of continuity we know that del dot j plus dou rho by dou t equal to 0, in which they substituted rho comma h. So rho comma h plus dou rho by dou t is equal to 0. So we know that the equation of motion, that is d rho by dt is equal to rho comma h Poisson bracket plus dou rho by dou t equal to 0. So from this they found that del dot j is equal to Poisson bracket of rho comma h, and then substituted, you got that is d-rho by dt equal to 0. So from this Liouville theorem, they got that is d-rho by dt is equal to 0. This is volume of phase space is equal to 0. This is an idea just behind this Liouville theorem. Next we have to find the properties of phase space. Okay, so what do you mean the properties of phase space? We want to study the properties of phase space. First property of phase space, that is density of phase space remains constant. So properties of phase space, in which first property, that is the density of phase space remains constant. The density of phase space is constant with respect to time. Okay, with respect to time, the density of phase space is constant, first property. Second property, the motion of particle in a phase space is analogous to the motion of non-viscous fluid in real space. The motion of particle in phase space, it is analogous to the motion of particle, that is motion of non-viscous fluid in real space. It is analogous to that. Okay, and the third property, that is two phase trajectories cannot intersect each other. Okay, can't intersect each other. So it can't intersect each other. So if you consider a phase trajectory like this, it can't like this. That is, the intersecting trajectories can't take as a phase space trajectory. And because the trajectories are well defined, and we have to understand some phase trajectories of one-dimensional box, linear harmonic oscillator, and phase-space diagram of elastic collision and inelastic collision, like that. So before that, you have to understand what is the properties of phase space. The density of phase space is constant with respect to time. The motion of particle, which is analogous to the in phase space, is analogous to the motion of non-viscous fluid in real space, and it can't intersect each other. Okay, so the trajectories are well defined for this phase space. Okay, so next we have to understand about the trajectories. Okay, so first of all, the one-dimensional box phase space. So one-dimensional box, we have two cases. We know that a one-dimensional box from 0 to L. So inside V is equal to 0. The potential inside is equal to 0. And we know that energy is equal to kinetic energy plus potential energy, in which for one-dimensional potential energy is equal to 0 inside. So P square by 2m is equal to E. P is equal to plus or minus under root 2me. So you know that space you have to find the momentum to find the phase space. Okay, so this is from 0 to L, and one dimensional box is like this. The phase space is, we have two values for the P values, that is plus under root 2me and minus under root 2me. This is momentum, this is position Q. Okay, so momentum is positive, so forward. Momentum is negative, so backward. Okay, so this is for the one-dimensional box phase space from 0 to L. Okay, next we have to find one-dimensional box from minus L to plus L. Here we can take like this, minus L by 2 to plus L by 2 also. Here also energy is equal to P square by 2m, because potential energy inside is equal to 0. So P is equal to plus or minus under root 2 me, but the phase space is like this. The position is changes because 0 to L by 2, and here it is minus L by 2, and here it is positive under root 2 me, positive, and this is negative under root 2 me points. So this is the phase space of phase space diagram for one dimensional box from minus L by 2 to plus L by 2. Okay, so you have to understand the way phase space is like this. Okay, so here it's like this. Okay, next we have to find the phase space diagram of linear harmonic oscillator. We know that linear harmonic oscillator like this, and there is a mass of Q, there is a position and change. Q is like this, Q is positive here, momentum here negative. Okay, so we know that because force is directly proportional to minus 6, A is directly proportional to minus 6 because force is equal to ma, so acceleration is directly proportional to minus 6. So this is mean point of this mass, and it is after a movement along x-axis, it returns to this same position opposite to the movement. Okay, so we know that the energy for linear harmonic oscillator, that is p square by 2m plus half kx square. So p square by 2me plus kx square divided by 2e is equal to 1. So p square divided by under root 2me all square plus x square divided by under root 2ek by all square is equal to 1. Why we write this form? Because this is form of ellipse. So we got that the phase space of linear harmonic oscillator is an ellipse. So this is p axis, this is q. So ellipse is the for linear harmonic oscillator. Okay, so this is all about clockwise ellipse is the because q is positive here, p is negative. So this considering clockwise ellipse is a linear harmonic oscillator phase space. And also if you consider that the linear harmonic oscillator which we put on this a beaker with a water, we are considering the linear harmonic inside a water in a beaker. So this is a damped oscillator. So the phase space is a ellipse because it but it is decreasing like this. Okay, so this is about the phase space diagram of the damped oscillator, because the amplitude is changing because it is in the place of water. Okay, next we are considering about the elastic collision. Elastic collision, in which you know that for before collision and after collision there is no loss of kinetic energy. Okay, so if you considering the collision, so there is a mass m which is moves there, and after collision it is comes there. So this is the same height. Okay, first collision is this, the same height, it will return to the same height. There is no loss of kinetic energy. We know that V is equal to mgh, that is potential energy. Okay, and energy is equal to p square by 2m plus mgh, because we are considering a mass at position h, the potential energy is equal to mgh and H can be written as mgq, p square by 2m plus mgq, and we have to find the position, we have to find the momentum. So at p is equal to 0, E is equal to mgq and q is equal to E by mg, and at q is equal to 0, E is equal to p square by 2m and E is equal to plus or minus under root 2me. So you got the points. So the phase space is like this. So when it is q, it is p. So when p is equal to 0, q is equal to E is equal to mgq. Okay, this is the point of mgq, maximum height. And if it is q is equal to 0, p is equal to plus or minus under root 2me. So this is like this, under root 2me, and the phase space diagram is like this, upward, and this is falling. Upward motion, this is falling motion. So this is about the phase space diagram of the elastic collision. So in elastic collision, if you consider the collision in which the height is decreasing after collision, in elastic collision it can't reaches the same height. So there is a loss of energy, kinetic energy is lost. So the phase space is like this, is q, this is p. So this is moving like this, and amplitude is decreasing, and because it is in elastic collision, energy is decreasing. So this is maximum is plus under root 2me, this minus under root 2me, but it can't intersect because it is a phase spaces can't intersect each other. And next we have to consider the phase space diagram of a particle with energy is equal to p square by 2m minus half kx square. Okay, so this is energy. So we have to find the position and the momentum points. So when you consider energy is equal to 0, p square by 2m is equal to half kx square, and p square is equal to kmx square. So x can be written as kmq square. So p is equal to, km is a constant, so p is equal to plus or minus cq. So it is in the form of y is equal to mx. So we have plus or minus cq. So we have get two lines here like this, because we got p is equal to plus or minus cq. So this is cq, this is minus cq line. So it is like this. Okay, so this is, we got the phase space diagram of that. And also we can consider p is equal to 0 point, so in which E is equal to minus half kq square. So q is equal to under root minus 2e by k. So this is, we got that is q must be real, so the position can't negative. So you can't consider this p is equal to 0. So you consider q is equal to 0, in which you got E is equal to p square by 2m. So p is equal to plus or minus under root 2me. So you got plus or minus under root 2me. So energy is positive. So you got the phase space diagram like this. This energy negative case, energy negative, this is energy positive case. So this is the phase space of the particle with the p square by 2m minus half kx square energy. Okay, And next we want to study about the ensemble theory and all. So first of all I want to say that is here in this class we have studied about the phase space and dimension of phase space, volume of unit cell, and then we have studied about the what we studied next. First of all, the dimension of phase space and the Liouville's theorem also we studied, that is density of phase space is equal to 0, and properties of phase space and phase space of several systems like one-dimensional boxes and linear harmonic oscillator and elastic and inelastic collisions, and also some special cases also we studied about in this class. So thank you for watching and keep learning. Thank you.